Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and our objective is to take a brief look at the contactor. A contactor is an electromechanical switch that serves as the principal interaction point between the control and power aspects of a motor control system. A contactor establishes or interrupts high current delivered to a motor, but does so only at the request of a low voltage control signal. An operator can use a low voltage pilot device, like a push button, to turn on or off a high voltage load, thus offering a level of isolation and safety. A contactor, paired with an overload element, form the two necessary components for a motor starter, being 1, a means of starting or stopping the motor, the contactor, and 2, a means of protecting the motor from sustained overload conditions, the overload. A contactor can be integrated with an overload in a single package called a motor starter, or the pair working together can be considered a motor starter. We'll take a brief look at both overload elements and integrated motor starters in later lectures. A contactor by itself cannot rightly be considered a motor starter since it lacks the means of protecting the motor from sustained overload conditions. A contactor is typically characterized by a set of moving contacts, hence the name, that make or break connection to a high-power electrical load like a three-phase AC industrial motor. These moving contacts are controlled by and electrically isolated from the low-power control signal provided by the coil. Additionally, sometimes auxiliary contacts serve to provide feedback about the state of a particular contactor. This is the schematic symbol for a contactor. These are the normally open power contacts from L1 to T1. These are the normally open power contacts from L2 to T2. These are the normally open power contacts from L3 to T3. A contactor is specified by the number of power contacts. It does not include the coil or any associated auxiliary contacts. This is a 3-pole contactor that would be used to make or break connection to an industrial motor supplied by either 208 volt or 480 volt 3-phase AC as representative examples. The L side is sometimes known as the line side. The T side is sometimes known as the load side. When closed by the low voltage control signal supplied to the coil, the passage from line to load is a conduit for muscle power. The contactor for electrically controlled systems incorporating motors is analogous to the solenoid-operated valve in an electrically controlled hydraulic system. The solenoid-operated valve conducts fluid power, but only at the behest of the low voltage control signal. This is the coil from A1 to A2, supplied not by high voltage source used to start a motor, but rather the low voltage control signal. The low voltage control signal could be 24 volts DC, 24 volts AC, or 120 volts AC as representative examples. This is the brains. A disclaimer before we continue. Always consult the manufacturer's datasheet for the specific contactor of interest. Do not for a moment assume the pinouts and specifications presented herein are universal in nature. A thick, tangled jungle of not only NEMA and IEC differences, but also manufacturer-specific terminal numbers and idiosyncrasies exist, especially for older contactors. This being said, most manufacturers now offer dual NEMA and IEC numbering schemes, with the IEC numbering scheme becoming more and more accepted because of its standardization and ease of interpretation. L1 to T1 might also be numbered 1 to 2, L2 to T2 might also be numbered 3 to 4, L3 to T3 might also be numbered 5 to 6. The coil is part of another electromechanical device known as a solenoid. A solenoid is an actuator, a term that means a device that takes one form of input and converts it into mechanical movement. In this case, the solenoid converts electrical energy of the control signal into linear mechanical movement via an armature, sometimes called a plunger. When the coil is energized by a low voltage control signal, the armature is pulled into the coil and the contacts attached to the moving plunger change from their deactivated state to their activated opposite state. In this case, the 3 normally open power contacts would close. Key to the operation of the contactor is the maintenance of electrical isolation between not only the coil signal and the high power contacts, i.e. the brain and the muscle, but also between the 3 independent high power contacts. L1 to T1 is a normally open switch, in no way, shape, or form electrically connected to the coil. The only link between the coil and any of the high power L2T contacts is a physical one, in that when the armature is pulled into the coil, these pairs close. Additionally, the L1 to T1 pair is in no way, shape, or form electrically connected to the L2 or T2 pair, or the L3 to T3 pair, or any other combination. They are three independent, normally open switches that, when moved by the armature, simultaneously close or open together. Used in this fashion, a contactor can energize or de-energize a high-power electrical load when instructed to do so by the low-voltage control signal. The brains tell the muscles when to move. Additionally, there sometimes exists an auxiliary contact rated for control level voltage used to provide feedback about the particular contactor state. This will be extremely useful when we learn about holding contacts and three-wire control in later lectures. This particular contactor has one set of auxiliary contacts. Since this is the first set of auxiliary contacts associated with this contactor, the first digit would be 1. Since it is a normally open switch, the second digit associated with these terminals is assigned 3 and 4. So the terminals for this auxiliary contact is 1314. We'll discuss terminal numbering in a later lecture. This is the IEC schematic symbol for a contactor. You can kind of see the similarities. This is the coil. The IEC schematic symbol makes it very clear the power contacts are controlled by the mechanical interlock with the coil. This is the normally open auxiliary contact, and these are the line and load terminals for the power contacts. Contactors are often permanently mounted in an electrical cabinet. Hardwired connections to the terminals are sometimes hidden inside plastic channels. Here is a 3-pole contactor. When it is in its deactivated state, the ohm meter indicates there is no connection between the L1 and T1 pair, nor the L2 and T2 pair, nor the L3 and T3 pair, nor is there any connection between any pair and any other pair. The three switches are open and electrically isolated from one another. These are the contacts designed to make or break connection to the power source. The ohm meter indicates the coil between A1 and A2 has a resistance just shy of 370 ohms. This coil is designed to operate on either 110 volt 50 Hz AC or 120 volt 60 Hz AC. Since connection of a certain magnitude characteristic of this coil exists, this coil should function as intended. An open coil would show no connection. A shorted coil would show no resistance. A damaged coil would show a different resistance. In either case, an open or short, the coil would not operate as intended. A damaged coil might operate poorly. The ohm meter indicates no connection between the 1-3 and 1-4 terminals of the normally open auxiliary contact as expected. Both the coil and auxiliary contact are designed to switch the low voltage control signals only. Magnetic contactors, as the name implies, are magnetically, not manually actuated via the low voltage control signal. If a technician wishes to test the functionality of a contactor prior to installation or during a maintenance, repair, or troubleshooting procedure, access to a portion of the plunger allows a means of manually actuating the contacts for inspection purposes. When manually actuated, an ohm meter indicates there is a connection between the L1 and T1 terminal pairs, as does L2 to T2 and L3 to T3. These switches have closed. Additionally, the ohm meter indicates the normally open auxiliary contact from 1-3 to 1-4 has closed. If the system warrants its inclusion, something known as an auxiliary contact block can be slid in position on top of the main contactor, actuated by the same plunger. Notice the slots in the face of the contactor and the accessible portion of the plunger match the back of the auxiliary contact block. As the plunger in the main contactor is pulled into the coil, clip pulls the plunger in the auxiliary contact block as well, and those switches associated with the block transition to their opposite activated state. This example auxiliary contact block contains 4 additional switches, 2 normally closed and 2 normally open. This is the second set of auxiliary contacts associated with this contactor, so the first digit of this terminal is given the number 2. Since it is a normally closed switch, it is assigned 1-2 for the second digit, for terminal numbers of 2-1 to 2-2. This is the third set of auxiliary contacts associated with this contactor, so the first digit of these terminals is given the number 3. Since it is a normally closed switch, it is assigned 1, 2 for the second digit, for terminals of 3, 1 to 3, 2. This is the fourth set of auxiliary contacts associated with this contactor, so the first digit of this terminals is given the number 4. Since it is a normally open switch, it is assigned 3, 4 for the second digit, for terminals of 4, 3 to 4, 4. This is the fifth set of auxiliary contacts associated with this contactor, so the first digit of these terminals is given the number 5. Since it is a normally open switch, it is assigned 3, 4 for the second digit, for terminal numbers of 5, 3 to 5, 4. These auxiliary contacts are rated for the switching of control signals, not power. These contacts are extremely useful for advanced control purposes, such as an electrical interlock, which prevents the coil of a contactor designated for reverse rotation from being energized while the one designated for forward rotation is energized. We'll discuss reversing motor starters with electrical interlocks in later lectures. Now that we've got an idea of how a contactor functions, let's examine the internal workings of a couple contactors and see if we can identify the parts that make them function. Let's start by removing the faceplate and examining the contacts. Notice the bifurcated or split contact on the left-hand side. This is the 1-3 to 1-4 normally open auxiliary contact for this particular contactor. It's designed to operate a low voltage control signal. The split is designed to prevent contact bounce. When we pop off the bottom of the contactor, we're rewarded with a view of the armature and the return spring. When the armature isn't energized, the return spring forces the contact upward and the normally open switches remain open. Notice the shading ring on the armature. This keeps the armature engaged during the zero crossing of an AC waveform and keeps any audible hum to a minimum. We can pull out the coil from the base. When energized, the armature would be pulled into the coil and the contact carrier attached to the armature closes the associated contacts. Here's quite literally an exploded view of a contactor that had a bad day. In this case, I've fully removed the contact carrier still attached to the armature. Notice one of the contacts is totally missing, and note the visible scoring on the faceplate and the coil. This contactor went phase to phase and suffered the consequences. We'll discuss mechanical, electrical, and push-button interlocks that can prevent this from occurring in later lectures. I like this picture because it really highlights how the low voltage control signal supplied to the coil is electrically isolated from the power contacts. The coil just pulls the armature into it and the contact carrier comes along for the ride. Here's another contactor with its overload element still attached. Working together, this pair would be considered a motor starter. It has a means of starting and stopping a motor, the contactor, and a means of protecting the motor from sustained overload conditions, the overload. We'll discuss overloads and motor starters in later lectures. We'll separate the contactor from the overload and pop the top off it to check the contacts. This is obviously a contactor designed to do some heavy lifting. Look at the surface area of these double break contacts. Despite its age, it looks like it's never been used. The base holds the stationary set of double break contacts. If we go back to take a look at the moving set of contacts in the top, notice the springs that cushion the impact upon closing. These springs are designed to minimize contact bounce. If we inspect the armature, we'll find an interesting mechanism. Rather than the armature directly driving the contact carrier linearly, it squeezes a lever mechanism. When de-energized, the spring in the mechanism pulls the armature out of the coil and opens the contacts. When energized, the armature is pulled into the coil and levers the mechanism to close the contacts. Here's the point of interaction for the armature and the contact carrier. When de-energized, the moving contacts are retracted and the connections are open. When energized, the moving contacts extend and the connections close. Here's a close-up view of another contactor's contacts in the open position, and another in the closed position. Again, notice the springs on the contacts maintains positive connection during rapid closure. This particular contactor does not have any auxiliary contacts associated with it, just the coil. Such contactors are often called dedicated purpose contactors. This is a 3-pole contactor, and the only control signal it needs is that provided to the coil. Dedicated purpose contactors are used for applications that don't require holding contacts or feedback about contactor status, as we'll learn in later lectures. Here's this same contactor disassembled. We find the linear actuation mechanism similar to our first contactor. When de-energized, the return spring keeps the armature retracted. When energized, the armature is pulled into the coil to close the contacts attached to the contact carrier. When de-energized, the return spring opens the contacts. Contactors and reversing starters work in pairs to run a motor either forward or reverse. The mechanical movement of the armature and a mechanical interlock between the paired contactors serves to protect systems requiring mutual exclusion between the two states. One would never attempt to rotate a motor both forward and reverse simultaneously. Not only does it not make sense, such an action would constitute a phase-to-phase event in the case of three-phase AC, an exceedingly dangerous and destructive event. Such a heinous condition could be prevented by two contactors in close proximity with a mechanical interlock between them. The movement of the forward plunger inserts a lever into the path of the reverse, and in the event the reverse coil is simultaneously energized, the lever prevents the movement of the reverse plunger. When the coil of one contactor has been pulled in, the mechanical interlock simply prevents the other contactor's plunger from moving, like sticking a foot in the door. Sometimes this is as simple as a plastic peg or lever, or complicated enough to require an additional interlock unit sandwiched between the contactors. When disassembled, we can see the levers on the interlock unit that slide into the ports on the side of the contactors on either side. Let us now discuss general specifications of coils and contactors and highlight some points of interest before we close up shop. The coil rated voltage must be matched to that of the control circuit voltage. A programmable logic controller with a 24-volt DC output cannot operate the coil of a contactor intended to operate on 120 volts AC. Either one must use a programmable logic controller capable of directly supplying 120 volt AC to directly operate the coil, or find a means of translating these two different voltage levels and flavors. Typically, such interaction occurs inside an interposing relay. It's basically a device that translates one's magnitude of input to a different level of output. We'll discuss both programmable logic controllers and interposing relays in later lectures. In addition to rated voltage, coils have a pickup, hold-in, and drop-out voltage. A pickup voltage is the minimum amount of voltage necessary to overcome the at-rest spring or gravitational resistance of the plunger. The hold-in voltage is the minimum voltage necessary for the coil to maintain the plunger in the activated position once it has been activated. As can be expected, the hold-in voltage to maintain a position is a little less than pickup voltage necessary to initiate movement to a new position. Finally, dropout voltage is the amount of voltage below which the coil just returns the contacts to their deactivated state. Again, coils with both the same AC and DC voltage rating are not interchangeable. Those with an understanding of reactance and impedance realize a coil of wire presents both a resistive and inductive impedance to an AC voltage source, whereas DC voltage sees only the resistive portion. Current draw for the same coil operated at AC versus DC voltages will be astoundingly different. Additionally, an AC coil experiences a slight inrush current upon being energized in comparison to that of its sealed-in or stable value. Additionally, since AC is characterized by a zero crossing, coils designed to be operated on AC include something known as a shading ring or a shading coil. These devices are inductively coupled to the main coil such that its resultant magnetic field is out of phase with the main coil. This ensures the plunger stays actuated and limits any audible hum. Finally, given the coil's operating principle is that of magnetism, when the current through the coil ceases, the magnetic field collapses in an effort to propel current in the same direction. This results in a voltage spike that can sometimes damage equipment. Sometimes a means of suppressing this voltage spike is included internal to the coil or must be externally attached to the contactor. Let's turn our attention from the coil to the rest of the contactor. The mechanical linkages, springs, and the contacts internal to the contactor must be periodically inspected for proper operation and signs of mechanical wear. Misalignment of the contact carrier or any obstructions will prevent movement of the contacts. Closure should ideally be as rapid as possible. However, contact bounce at closing can form an arc. When contacts open, there must be a means of rapidly extinguishing the arc that can form between two high voltage points in close proximity. The intense heat of the arc can erode and pit the contacts and vaporize or melt the conductive surfaces. The return spring in the armature is designed to force the contacts apart when the coil is de-energized. This rapid and forceful separation means the arc that could potentially form between them is given less of a chance to do so. Additional precautions are often used to minimize this arc. High-power contactors use arc chutes to divide and cool the arc. Blowout coils or other magnetic means deflect the arc into the arc chute. Vacuum contactors have nothing inside them to ionize in the first place, and the arc is extinguished upon opening. All these methods share the same goal. They terminate arc current very quickly. The contacts of a contactor have three typical current ratings dependent upon application: make, break, and continuous current carrying capacity. Inductive loads like motors experience an inrush current several times their normal current draw. Contactors switching these types of loads must be sized to accommodate this phenomenon during closure and opening. Numerous factors must be considered when sizing contactors for a system, including the difference between DC versus AC loads, the magnitude of the voltage and the current being switched, and the nature of the electrical load being switched and the application. AC voltage is characterized by repeated passage through a zero point between cyclical shifts in polarity. This means an AC arc extinguishes earlier than a DC arc, which does not have a zero crossing. Contactors rated for DC must be physically larger than AC contactors for the same level of current to account for this reality. High voltage and higher currents will require contactors with higher power ratings. Resistive, nonlinear, capacitive, or inductive loads present a different relationship of current to voltage. An inductive load, similar to the previously discussed coil, is characterized by the presence of a magnetic field. If the current is switched off, the collapsing magnetic field in the load can cause a great voltage spike if it is not properly suppressed. Finally, the specific application of the contactor must be considered. Repeated opening and closure during locked rotor conditions will electrically wear the contacts. A locked rotor is a motor at rest. When first energized, a motor experiences an inrush current, often 6 times in excess of its regular full load current, for reasons I'll explain in other lectures. A motor that is being jogged or inched means the motor is only briefly energized and allowed to return to locked rotor or partially locked rotor conditions before being energized again. Plugging is the intentional disconnection and sudden reversal of a motor spinning in a particular direction in an effort to bring it to a quick halt. You better believe such an event is associated with an extreme current draw. Motors that are jogged or plugged often will experience excessive contact wear, and contactors designated for this purpose must be used for this application. The IEC divides contactors into utilization categories. For example, a contactor with an AC1 utilization is designed to make or break connection for only slightly inductive loads, such as resistive heating elements. A contactor with an AC3 utilization is designed to make locked rotor current and only break full load current and only occasionally jog. A contactor with an AC4 utilization is designed to make and break locked rotor current and jog and plug. For example, a certain contactor sized for 550 to 575 volts is designed to handle 18.5 kilowatts and 28 amps when used for AC3 purposes. However, this same contactor can only handle 11 kilowatts and 17 amps when used for AC4 purposes. In contrast, NEMA contactors are given size ratings based on current, voltage, and power, since an operator may not know the planned application or the duty cycle of a load. NEMA contactors are built with sufficient reserve capacity such that each contactor spans a larger usable range. This really highlights the distinction between NEMA and IEC philosophies, that of robustness, interchangeability, and generality versus specificity, purpose, and limited scope. This, depending upon your perspective, can be viewed as an advantage or disadvantage. A NEMA contactor, since it spans a larger usable range, will be more robust, however larger, heavier, and more expensive. An IEC contactor, since it is a special purpose built device, will be smaller, lighter, and less expensive. However, it is not as flexible nor robust over such a wide range since they are application sensitive. Finally, special purpose and solid state contactors exist, with notable differences between the ones I used as examples. The contactors we examined were electrically held contactors, in that the coil must continually be energized for the power contacts to remain closed. If the coil lost current, the contacts would open. Additionally, there exist mechanically held contactors that require two coils to operate, one being a latch coil, the other being an unlatched coil. The latch coil is momentary in nature, and when energized, simply moves the contacts into a position a mechanical means can then hold them together. The loss of current to the latch coil does not affect the position of the contacts, and they remain closed. Only when the unlatched coil is energized, again with a momentary pulse of current, do the contacts again open. A solid state contactor is also a means of establishing and interrupting current to an electrical load. However, it does so via non-mechanical means. The principal disadvantage of contactors is that they are composed of moving parts that can wear out. Additionally, a contactor, being made of moving parts, can only switch so fast before contact bounce becomes an issue. Enter the solid state contactor. This is a device with no moving parts that can not only switch on or off an electrical load at speeds much greater than an electromechanical contactor, thereby influencing a driven load's operating characteristics, but also do so at key times. Again, consider an inductive load containing a magnetic field. If the current is suddenly terminated, the collapsing magnetic field could generate a large voltage spike to keep current traveling in the same direction. A solid-state contactor with zero crossing detection will purposely extend the closure of the device past the receipt of an open command until the next zero current crossing to prevent this event from happening. We'll return to discuss solid-state contactors, soft starters, SCRs, and thyristors in later lectures. This wraps up our brief introduction to the contactor. We'll be making use of this device in later lectures as the principal interaction point between the control and power aspects of an electrically controlled system. In conclusion, this lecture took a brief look at the contactor. We identified the contacts, the coil, and the auxiliary contacts in both the schematic and representative examples and discussed the purposes and function of each. Additionally, we discussed auxiliary contact blocks, armatures, contact carriers, shading coils, mechanical interlocks, and discussed coil and contactor specifications and construction, utilization categories and sizing, means of extinguishing arcs, and contrasted general-purpose electrically held contactors with mechanically held contactors and solid-state contactors. Remember to review these concepts as often as you need to really drive it home. Imagine how well a lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.